Yeah, so like I was saying, today we're going to be looking at the concept of lattice energy and the Born-Haber cycle, right? I know many of you, obviously most of you, don't know it, and we're going to go through the basics, right? I want you to turn to page 12. On page 12 at the top, it is showing us the metallic bond, right? A metal-metal bond. The high thermal electrical conductivities of metals are due to the presence of free electrons. That's why metals conduct electricity easily, because of the free electrons and the bonds created by the free electrons, right? Right now, let's go to the next paragraph. There they say, consider the reaction between sodium and chlorine. Right? Experiments show that 410.9 kilojoules of heat are evolved when 1 mole of sodium chloride is formed. So basically, remember, what does evolved mean? Evolved.
Changes to state.
Okay, to change, right? But in terms of this year, is to release. I want you to write that down or give off. Let's write that on top of evolve, release or give off. We're looking at this thing, this paragraph here. No, sorry, in the notes here. What's here? On page, what's it, 12. Yeah, on the top here. Remember you learned about exothermic reactions and endothermic?
Yeah.
Right.
Give up it, picture. Let's go on.
Give off.
So it's exothermic. So evolve is exothermic.
Yeah, let's go with it. So, right, so when you have an exothermic reaction or an endothermic reaction, it tells you what's going on in the reaction. Whether the reaction is giving off heat or taking in heat. So whenever we hear the word exothermic, the EX will tell us that heat is being given off, right? Endo means heat is given in the reaction. So sometimes, remember, we usually need heat to actually break bonds, but it can also create energy for the bonds to create. Heat is used to break bonds, but also create bonds. So with different reactions, and then with the nature of the reactions, we get different types of energies. Now, we're going to be looking today at those types of energies, right? And we're going to I think we're going to use the salt compound as an example and looking at the different energies. Now, in this textbook, they've got all the actual definitions, but it's hard to understand it. It's kind of hard to understand. But we're going to go through the textbook example first. Then what we're going to do is go over the additional notes. After the additional notes, you're going to look at the videos, because maybe when I'm explaining it here, it's still a bit complicated. But we've got like grade 10 and grade 10 videos that we uploaded here. So we're going to watch it together and we're going to look at it, right? So let's look at the example, right? So we're looking at salt. You all know salt, right? In its normal form, what is it? Solid, liquid, gas? It's solid, right? So salt is a solid, right? But in the natural form, sodium occurs as what? As a? No. What does the S stand for? The S stands for? Solid. Right? So sodium occurs naturally as a solid. Chlorine occurs naturally as a gas. So when you're reading these equations, if you're not familiar with it, the S is telling you solid, the G is telling you gas. There's something else that we have. It's AQ. Aqueous. Right? It's telling you the form it's in. Right? So it either can be in a solid, gas, or aqueous. Right? In this particular example, we consider the reaction between sodium and chlorine. Experiments show that 410.9 kilojoules of heat is evolved when 1 mole of sodium chloride is formed from the solid sodium and gaseous chlorine at 25 degrees and 1 atmosphere pressure. Right? We've got delta H here, and we've got minus 410.9 kilojoules. So what does that mean?
It gives off.
So the minus sign. So I want you to write down the minus sign, the negative. I think that's What's that phone inside here? No.
Next up. What's next up?
Yeah.
That's loud, eh?
Negative will be endothermic.
No, negative is exothermic. Gives off.
Exo. What about reactions where it requires heat and all of a sudden gives off heat?
Yeah, but that's
What's that
what we're
mean?
doing now. Stages, at each stage we will work out
Yeah, but what you
where it gives out. You have to look at the resultant, what the net at the end, whether it's higher or lower.
That one there, when it happens when you're balancing out the equations. Remember when you're balancing out the equations? So if we find that on your left hand side, you got the endothermic or exothermic, or the right hand side, you find you got the endothermic. So it can change.
So that's what we're
it
doing
might
now.
have both exo and endo.
Read off the charge. Minus 4 and
So what does that mean? What does
It's
it
off the chart.
I
You have to read it off the
just
chart.
on the equations.
Charge here.
No,
Energy.
we're gonna work it out now.
That's
a very good example.
I don't think it's a calculation.
No, it's a calculation. We're gonna calculate it now.
Someone was doing
Page
work.
14. No, just all of us to read this thing.
Mina ngiyabakhumbula amagama kodwa ukuthi wawenza kanjani kodwa yabiza igama ngiqaphilizwa where I was 23 years ago futhi yena
So add that to another two.
another two.
You're gonna have to make time.
I know, it's just like hard because it's not something to be doing. Not just sit stuff.
I stopped watching my Netflix.
I don't even watch TV. Since I left work, I think one day I watched. I don't even watch.
This is I'm really
That's
then I go and
4 years.
watch something.
Yeah.
I don't have anything anymore.
But I haven't looked at Netflix in a while.
ufuna ukushintsha
And
ufuna
then
ukuzana
I'm really needing what I
Eh?
watch.
downgrade ya
I was really,
angene umuntu we-TV
want to watch that. It's not really entertaining.
angene umuntu we-TV manje abantu bebedala ukuthi ngikuzoyonke ama-channel abashayo
Anything.
and soon mhlawumbe maybe end of this month bayahamba so
Yeah.
ngisawuvulelani ama-channel ngisawasebenzisa
Really.
1,000 ngemonth
Extra views,
no ya kunama-channels ngaba ama-channels
Service now called. Internet shuffle.
that's an hour,
During that time, you go watch a movie.
89.
It's not expensive. Okay, the ticket is
Yeah,
fine.
That's why man.
No answer.
No. Yeah.
70 bucks or 79 then or whatever. Movie ticket.
Everything.
Any day,
Everything.
anytime.
Oh, this company.
Yeah, long as you have a net card, half price. Whatever the ticket is, popcorn,
And they have each month.
half.
And because it works out to around about 200 then.
For something.
Well,
How much are you
what happens
paying?
is here.
Oh,
Now if you
Ngibona ngoba uhlala iy'ngane ayikubeni feyivula i-TV mhlawumbe kuke 10 minutes idlale uyicishe ibuye feyizivumi zihlale lo 10 minutes zishiye zihambe
What did you like? I think it was I was thinking.
I'm actually wanting to go watch a movie.
Yeah.
nami ngibuka kodwa nje kuba isikhathi
Apparently
manje
there's new
manje sakubona
No, but they're doing.
How much more
No,
much
I
I
think it's ever since the last two movies where they're doing, they're doing some really.
no, but
That's
they
it.
bring some reviews.
No,
So I don't go with reviewers, you know, like like only watch romantic drama movies. So if you check
drama movie amadala isikhathi
drama movies, romantic, they will have high rating. Yeah, but
unrealistic.
if you're a Fast and Furious fan,
Yeah.
you will view it. Someone that likes drama movies,
Who's
that's
gonna
not why
tell
you
you?
like
Everybody
it.
seems to be included or fans because
No,
everyone's
that's
like,
what
Yeah.
it is.
The original.
They're not really
everyone's,
bad.
yes, everyone's
The
everyone's
fans,
waiting was waiting.
No, the originals was far missing.
Yeah.
You know, the first one or
That's
two
why
or
it's
three.
Fast and Furious.
Now
Mm.
it's like. It's
You
like
watched it?
no, but the
the
previous
last
ones.
one.
I'm scared to
Not
watch it
the
now
last
because they still apparently.
Yeah, I'm
it's
not, I'm
like-
not gonna waste my time with it.
He jumps across a bridge and he caught her in the air and he landed on the car and it was fine. The last
That
one.
was the last one.
That was eight.
Or going with the car and flying into space or something. There was some scene.
Yeah, there was some.
Yeah, last one. What?
Yeah, realistically now
But
it's
I
like
think
it's,
it's,
yeah,
they're all over there.
yeah, they should have.
Yeah, so like I say, we looking at the example in here.
Even the one. No, it's.
Right, so if we're looking back now, guys, so we said that the negative tells us that heat is being given off. So what would the positive tell us?
It's a big
Yes. Positive, that heat being absorbed. Now we've got a solid sodium coming in contact with a half chlorine. So basically it's Cl2. So that will actually give us one chlorine molecule, right? Half of 2 chlorine molecules will give us 1, right? So we end up with a bond. What type of bond is that, Nikki? Got a positive and a negative. What type of bond? Temba? Ionic. Don't,
Yeah.
over the ionic.
Ionic bond.
A positive, right? The
Yeah,
bond is
it's
changed.
ionic bond.
Yeah, remember, ionic, right, or electrovalent,
Electrovalent.
it's the same word, right?
Yeah.
Electron transfer.
Yeah, I think I told you, right?
Yes, it is.
Ionic bond, it's when a positive element combines with a negative element. Right, and the positive element is usually a metal, while the negative element is a non-metal. The metals are found on the far left-hand side of the periodic table, while the non-metals are found on the far right-hand side. Right?
I thought it was another way around. The metals
No,
are on the right.
No, it's not like just.
I said I thought. What's wrong with you?
We've been asking that conversation for a long time.
Relax, guys. Yeah, so anyway, this is an ionic bond, right? And this is what's occurring here. We've got a positive and negative molecule, and then we can see the charge on the molecules when they combine, right? And they say energy, note, energy is involved is shown with a negative sign, right? And delta H is negative, energy absorbed is shown with a positive sign, right? The reaction can be broken down into a number of hypothetical stages, each one involving an energy change as outlined, right? The algebraic sum of the individual changes must be the same and the experimental determined value. This is the principle of conservation of energy, right? You all understand the principle of conservation of energy? Basically, what goes in must come out. Energy cannot be created or destroyed, it's merely transformed from one form to another.
Yeah.
Right?
This is that 8 thing.
Yeah. That's it. Right, so now, so we looked at it like, we looked at the overall reaction. Now we're going to look at it in terms of each step of the energy. So remember, sodium was a solid, but we ended up with what?
Yes.
Yes.
We ended up with sodium becoming a gas. Because, why would it become a gas? Why do we need sodium to become a gas?
We just need to combine with chlorine, which is a gas.
Yes, that's the reason. We need to combine it with chlorine. Chlorine is a gas. In order for the bond to occur, they must occur in the same phase. So we need sodium from a solid to get it into the gas. So, y'all know, how do we take a solid and convert it to a gas? We heat it up. Remember Saturday, guys, we looked at the 3 phases of matter,
Yeah.
right? And I said, we looked at an example of H2O. You weren't here, but it's basic stuff, right? So, we looked at an example of H2O. To convert H2O from a solid to a liquid, what do? We add heat. Now, to convert a liquid to a gas, we add?
Heat again.
But how do we go from a solid straight to a gas? Solid straight to a gas. Dry ice. You know dry ice?
Sublimation.
Sublimation.
Right. That energy is called sublimation energy. When we're moving from a solid into a gas. So that's what's happening here with sodium. What are we doing? We are moving from a solid to a gas. So we need lots of energy to do that conversion because we are breaking the bonds. We are taking a solid. Remember, solid particles are closely packed. Now gas particles are far apart. So we need to break that solid with high amounts of heat energy to convert it into a gas. We need to get it involved, right? So let's look at the amount of energy that's taken in to convert sodium solid to a gas. All right, let's look at that there. The conversion of sodium solid into a gas is sodium atoms, right? The energy needed to break down the metallic lattice of sodium. This is called the sublimation energy. You guys have said it, right? And the sublimation energy is given by the symbol S, right? Sublimation energy is given by the symbol S.
While we here,
Yeah, bro.
can you explain mole?
Mole.
And according to the periodic table,
But it's got nothing to
nothing, we're not going
with
to use mole.
We can use it, but not in this year.
Not in this year.
Yeah, I'm gonna be. It's going for me going off topic now.
Okay.
Sorry, I just missed something. Have we done it, Joe?
Yeah.
Okay. The negative, you know, the energy, negative,
Yeah.
would that be exotherm?
Yeah.
Okay, positive is end of it.
Yeah. I had it on the board.
No, so I just went out there.
Yeah. So we're looking at converting. Remember, we said that we want this reaction to occur, and we need sodium in the gas form. In order to move sodium to the gas form, we need to sodium to take in some energy to convert the solid to a gas, which is called sublimation energy, right? So you can see that the total amount of sublimation energy is 108.7 kilojoules per mole. I think Trev is asking what is a mole, right? Does anybody else not know what a mole is? It's a unit of measurement.
Mass or something?
Yeah, so mole, right? I'm just going to write it here. N is equal to mass over molar mass.
Volume.
This here is your mole, right? This is your mass, right? This is your molar mass. And the molar mass, this is measured in grams. This is measured in grams per mole. And this is measured in moles. Right? That's it. Right, so when we're looking at 108 kilojoules per mole, they're looking at the amount of molecule we have, or the amount of element we have. Right, so for this sodium, we'll need 108.7 kilojoules for that mole. But we'll look at this later on how to do some calculation. But like I said, I'll be going off topic now to go into that. But this, for now, you need to know it's a unit of measurement. That's how you get like energy we're measuring in kilojoules, right? It's this year, the amount of sodium is measured in moles. Do you get it?
Yeah.
Right? So yeah, let's go to the next line, right? So we know the sublimation occurred and we got sodium into sodium gas, right? And then we've got 1.22, the removal of valence electrons of sodium atom to give a sodium ion. So we then have to remove valence electrons. So remember, the charge on this sodium is currently 0, right? The charge on the sodium is currently 0. Now, if we remove one electron. Remember what Bilal asked me? Is the number of protons and electrons equal?
Yes.
Right, so the overall charge, remember? We said, let's say for sodium, if we go to sodium, find it on the periodic table for me, Benny.
That's fine.
Yeah, and give me the,
So these positive 1.
so it's positive 1. Right? So how many electrons?
Maybe one.
1 electron. How many protons?
We have that one.
1 proton.
Right. So, if we're looking at this here, if we remove 1 electron, the charge is 0 at the moment. Right. If we're going to remove 1 electron, what's going to happen to this? If we take out 1 electron there, what's going to be left?
Positively charged.
Yeah, that's what's happening. So we got 1 electron, 1 proton, and this is equal to 0. Right, now we're removing this here. So, no longer negatively charged, it's going to go plus 1. Is everyone with me?
Yeah.
Right? So this is what's happening here. We got the sodium, which is 0, right? And now, remember, we added from solid, we got it into gas form. We had the second step. Now, we're looking at, it's lost 1 electron. So it became positively charged. And because it's only 1 proton, what do we write here? We just write plus. We don't need to show the 1. You just write 1, just write plus, right? And then it's still, we remove the electron, but the electron is still there. Plus 1 electron, right? Now, the removal of 1 electron, right, is known as ionization energy. When you remove an electron, it is known as? So basically, you're taking a zero form, right? So it's taking a octet or a non-reactive element, and you breaking it into ions. Ions can either be positive or negative. So that's why we're calling it ionization energy, because we took this non-reactive sodium and we broke it down into positive and negative. So this is known as ionization, right? This is known as?
Give another example.
And the ionization energy is given by I. You can see how we got sublimation energy is S, ionization energy is given by I. And what's the amount of ionization energy there? It's
493.8 kilojoules per mole.
I is equal to 4, positive 4. So what does that tell us, Benny? Is it taking in, for it to convert to this here, is it taking in energy, giving off energy? Taking in energy. Right, the amount of energy taken in was 493.8 kilojoules per mole. Now let's go to step 3. So this was step 2. Now we're going to step 3. And I'm writing it out here just to further explain, but everything is in there, right? Just writing to further explain so you can understand. But I'm just gonna stop, because there's everybody. Pamana, you're right.
Yeah, no, no.
Right. You okay? Eh? And Tempa, you're right there. Alright, so let's move on. Yeah, so 1.2.3. Now we're looking at something called dissociation, right, of the chlorine molecule. So we worked on the sodium. We got sodium into gas form, and we got it into its ionization form. Now we're going to look at the chlorine, right? So dissociation of chlorine molecule into chlorine atoms, right? So the energy is needed to break the covalent bond, because remember, chlorine occurs naturally as a dative bond. Basically, it's two chlorine together, right? Chlorine, you can see that it's actually two chlorine together. But do we want two chlorine together? No. We just want a single chlorine in gas form, right? So the energy needed to break the covalent bond between that two chlorine is known as the dissociation energy, right? And what type of bond are we breaking here? What type of bond? And why we say it's a covalent bond? We said ionic bond is between a positive and a negative. Covalent is a sharing of electrons, usually between two negative elements.
Yes.
Usually between two negative elements. So we got chlorine and chlorine, both are right. So we are breaking the covalent bond, right? So the amount of energy used to break this covalent bond is known as what?
Dissociation.
Yeah.
Dissociation.
Okay, let's draw and check it out here. Board CO2 gas into chlorine gas. Right. Now, and this is known, remember the D is equal to this. Right, this association energy. Right? Now there's something important that we need to note here. What is going on there? They say D is the energy needed to convert 1 mole of chlorine, right? Need to convert 1 mole of chlorine molecule into 2 moles of chlorine atoms in their state of lowest energy. To give 1 chlorine atom, half the dissociation energy is required, right? Remember, we got 2 chlorine here. So we only need 1. So we want the energy for 1 chlorine. Therefore, we take the dissociation energy and we divide it by 2. Right? So therefore, we take D over 2, which will give us positive 120.9 kilojoules.
All these energies, is it different for each element? Or
Yeah,
is
it's
it-
different. It's called a half reaction table.
Yeah.
So, this side note here, right? Half reaction table will give you I don't know if you all remember. I'm sorry, man. I even forgot that you don't know that. Sorry, man. So there's a half reaction table. It's usually found in the back of the periodic table that will give you all the energies for elements and compounds widely used in inorganic chemistry. Right?
The back of the periodic table.
Yeah. So it's not all periodic tables have it. Let's see your periodic table. Oh no, that's not that.
There was nothing in the back.
Okay, let me show you guys. Right? On the
You mean the ones you buy? Periodic tables you buy?
yeah. It's a special one. You buy it. You got kids. What grade?
Grade.
In natural science.
7.
In natural science, in grade 8, they give them the table.
Is it?
Yeah.
With the
Anyone
table.
have all the kids?
Three.
Yeah.
Can you buy from the stationery shop?
How?
She finished her class.
Oh, she probably won't have the stuff. Yeah.
Or can you get it from
Yeah,
the
it's
stationery
from
shop?
the stationery shop, but it's on the internet. I'll just show you guys. I'll print it out. Maybe I'll print it out now. Sorry, man. I just forgot to. But I'm just, by the way, this, it doesn't come out though. Although, but you need to know the background of this, right? We're going to look at it further in, what's this, our, when we do cation and look at cations and anions.
Oh, this is in the past paper, this? In the, that,
Given, yeah.
yeah, it gives you the, but it's electrode potential.
Yeah, let me print out this one.
You printing it out, have you?
Yeah.
Why don't you print out the PRI table like that?
Okay.
Maybe on one side, PRI
Yeah.
paper and
Collate means back to back. So I must take collate out.
Collate means
Single.
packing them back. You pay 2 pages to put them together.
That was this collating there. So,
Yeah.
for sure, yeah. It's always okay.
Even if it's not true, Trevor will change to make sure that Trevor is
so.
It should be one that is fit.
We don't need all the ionization energies and all those so, right?
Sorry?
You know, in the block normally you get the
Yeah, so the this thing, you guys for this, nothing comes out in terms of that there. But you'll have to learn, like they usually might ask you like this specific example. And then we look at the bond neighbor process And we'll look at into that there, after we're done with this. It's the same thing. It's only this example that they look at.
Avi,
Yeah.
on the metals and non-metals, which one you said was the one that donates? Which one was the one that received the electrons?
The metals then?
Metals and non-metals.
So metal gives off the electron.
Yeah.
The
But what I said over here is that the sodium is basically it's not neither positive or negative charge.
Yeah, no.
But in terms of whether it's a metal or not, it's a metal.
Yeah,
Yeah.
one of the properties of the metals and non-metals, we said the metals normally get donate or they accept electrons. Which is which?
So you remember positive and negative on the periodic table.
Yeah.
So your
The metals give off.
left hand side was a positive and the right hand side was a
No,
negative.
but like in
So-
what in context of what
This
what
is
are you
scale of
asking
more.
this from? Where you?
I remember the time when we had the periodic table and you.
Oh, I said there's a step.
So,
And I was telling you that what I was telling you this year, positive elements from the far left will combine with negative elements from the far right to create an ionic bond, a metal and a non-metal.
Yeah. So now.
Yeah.
Remember,
So it's
remember
a
the time
transfer.
when
It's a transfer of electrons.
yes. Remember the time when you gave us the example of water
Yeah,
H2O,
yeah,
and then you said that the H is on this side, the oxygen is on this side,
right.
and then you said that one gives off and the other one receives.
Oh yeah, the transfer.
Yes.
Yeah, so the transfer occurs from the metal to the non-metal.
Okay.
Right? Remember, we even looked at it in here.
Mm.
I showed you all how the transfer occurs, the ionic bond.
We need to do the orbital.
Yeah.
Yeah, you do the
It
orbital.
was, I can't remember what, if we turn to page 6, we're looking at lithium and fluorine. The one electron, valence electron from lithium moved to fluorine. You can remember?
Yeah.
Turn to page 6 in the bottom there. You got lithium and fluorine. And then you can see the positive lithium. Basically, lithium is a metal, fluorine is a non-metal. And then we see that one valence electron from the lithium moves to the fluorine.
Yeah.
And then when something loses the electron, it becomes positive. And once something gains the electron, it becomes negative. So basically, the lithium became positive because it lost an electron, and the fluorine became more negative because it gained an electron.
Yeah.
Yeah. So you can, if you want, you can take down the example.
Okay.
I think we should just only do chemistry and if you can plant the rest. So what you say?
Yes.
The young people just bear with us, right? We haven't done this in a long time. Just bear with us.
Well, they're not getting irritated with us. All the questions, stupid questions. Chemistry is, I tell you something, chemistry is just examples. You learn that. Sometimes, I feel sometimes you need to stop and just do some examples. Not too much of reading and theory. Because you know what will happen? You get that. I'll give you an example. exactly what it's doing.
Three.
Taking his
Yeah.
This one is easy, but you can get this one. Falling gases is as in that magnet fix to oxygen. Yeah, we only got oxygen. Strongest acid.
Let's take one and pass it.
What's that good stuff?
Right. Let's continue.
Yes.
Yeah. You want me?
Right guys, let's go back. Let's go. We at dissociation energy. Now we're moving to addition of an electron. So we are number 4. Yeah, it takes some time to get used to, but once you learn it, it's not going to be that hard once you know the background, right? So, 1, 2, 3, 4. Right. Now we're looking at, we've got the chlorine, right, into chlorine gas. Now we're looking at converting the chlorine, right, into an negative. So basically, this process of chlorine is actually exothermic, right? The energy involved in adding an electron to an atom of an electron is called electron affinity. So basically, we got chlorine gas. We want to make the chlorine gas negative. How do we make the chlorine gas negative? By adding an electron. So basically, it gains an electron. And remember what we said, Shemba? When something gains an electron, it becomes?
Negative.
Yes. So basically it's this here. You can see this E here is actually going there because it was one electron that went over. If we had 2 here, what's going to be the charge here?
2 minus.
Right, well done. Right, and this is called E. And the amount of electron affinity is equal to Negative 379.5 kilojoules per mole. Right? Now let's go to the next one, 1.2.5. At 1.2.5, we are looking at liberating energy. Now, so this is where the actual bond comes in. This is where the actual bond comes in. So we remember we got sodium in its current state as a positive and as a gas. We got chlorine as a negative and as a gas, right? And when they combine, they form Na plus Cl minus, right? And this is the interesting thing that happens. When these two gases combine, they form a solid, which is a precipitate. It's called a precipitate. When you're taking, it's like, you remember how do we convert steam into liquid? Condensation, right? And how do we convert liquid now into solid? Freeze it, right? But what's happening with the temperatures now?
It's coming down.
It's decreasing, right? So, what will happen here? We're converting a gas into a solid. What will we need to? We need to remember these particles as a gas. It's excited. It's everywhere. Now we're going to bring them back together.
We need to give off energy.
Yes, we need to give off that energy. Take out the excitement from the gas. The gas particles are just jumping around. Now we're going to take out we're going to take out the excitement and we're making them come back together to form a solid. So therefore, a lot of energy will be taken away. Right. And the amount of energy is called lattice energy. This is the total amount of energy, right? Your lattice energy. U is your lattice energy. Right? And you can see the amount, you can see it's quite a big amount of energy there compared to everything else there. It is minus 754.8 kilojoules. Now, if we look at the overall complete reaction, so basically we're looking at our change in energy from the start of this process to the end of the process. Delta H, our change in entropy. Yeah. Which means?
Change in.
Yeah. But we don't cover it. Yeah. Right, so we're just looking at the change of energy and we're going to add up all our half reactions in terms of the energy, right? So the first one remember, let's go back to the first one we had was our positives. We'll work with our positives. We got positive 108.7. Where's the 108.7 coming from?
Starts in sodium, so yes.
Yeah, so this is from our sublimation energy. So we'll put an S on top there, right? We're going to put an S on top of that, right? And then the next one we've got plus 493.8. 493.8, what energy is that called?
Ionization.
Ionization, right? And let's go to the next one, 120.9.
Dissociation.
Right? And the next one, we've got minus here, right? But remember, it's all pluses, a positive, and then, but this is minus. Positive times a negative is a negative. So therefore, I'll put the positive here for now, but we'll put the negative in brackets, right? And what is 379.5, which is our
Electron
Yeah.
affinity.
right? And the last one there is
Lattice.
So if we look at this here, in terms of abbreviations, right? It's going to be S plus I plus D, right? Plus, usually it's minus E plus minus U. Right, so that's our formula.
So electron efficiency will always be negative, and your lattice will
Yeah.
always be negative.
Remember, it's converting whenever we try to convert into a gas, I mean to a solid. We're taking out the excited or energy from the gas particle and we're bringing it down, releasing energy basically.
So this half reaction is only for the electrons.
Yeah, basically it tells you about the electrons. And then in terms of the energies, if it's in a question, they'll give it to you.
They'll give it to you.
Yeah.
Because I'm wondering how you get from
Yeah.
here,
To the energies.
Yeah.
Yeah, the energies will be given.
it'll be given.
Yeah. But you need to know what's happening with the energies.
Yeah, so you
So you know, if you're talking about ionization or lattice, you need to know what they're doing. When it's moving to a solid, to a liquid, you know, like that sort of thing.
So will they give it to you and plus and minuses, or you have to figure
No,
out the
they'll give
plus
you
and
the
minuses?
plus and minuses. Yeah, but what they want you to find out in the overall.
So they want you to write down like this
Yeah,
equation
yeah,
and
Yeah.
give you the answer.
So if we look at the overall change in the complete reaction, delta H2, right? We see that delta HT must be equal to delta H because of the law of conservation of energy. Remember what I said? Whatever comes in must come out, right? The individual energies involved in this reaction are set out in figure 1.3, right? What we're going to do now is go over we're going to go over this. Y'all are okay now? Y'all got the basics? Now let's get into more detail.
Would we be wanting to draw this?
Usually, yeah, sometimes they ask you, but recently they haven't been asking you. Might be, they have asked in the past to draw that diagram.
Okay.
Yeah, it's like
So it's just taking
12
this
mark
and
or 15 mark.
putting it on the graph here.
Yeah,
What's concerning me,
yeah.
we've got there's a lot of information that we're going through, but I haven't seen any questions or anything, so we don't know what to expect.
Yeah,
So,
so yeah, if we let's see if you go into the, I think towards the end of this module is an activity.
Okay.
But this textbook here, the activities are not going to end. So if we look at it, go to number 10 on page 30. Read out first, Pilar.
By using the calculus, the show that energy related to 1 mole of the calcium reacts with 40 molecules, give calcium chloride is greater than that for the hypothetical formula of the calcium positive and minus. What is the most important energy term which favors calcium rather than calcium?
And then they give us all the half reactions here. And they give us energy. So basically, they want you to work out the exact same thing that we worked out. But like what I told you, Benny, once you, so if you know this formula here, right? And then you got this, remember you know what's SI, and then if you work out this here, we can work out whether energy was given off or taken in our final answer to create the molecule. How would we know whether the energy is given off or taken in to create the molecule? Seva. We've got the formula. There's the formula here.
Alright.
How do we know?
if it's taken off, then you get a negative number.
Right, that's it. The sign. But yeah, but then you also need to know this here. If you don't know this here, then it's, you won't understand. You're just gonna lose marks there.
So this question here is just going to add everything up,
Yeah.
but instead of
Now, so the question is, what is the most important energy term which favors Ca2Cl2 rather than CaCl?
Yeah.
So what you just write down which energy?
Yeah, so they say, so they're given the data, right? So you got all the data, right? All the energies, ionization, sublimation, lattice energy, dissociation, and so on, right? Then they say, show that the energy liberated when 1 mole of calcium reacts, right? 1 mole of calcium reacts with chlorine molecules to give you the final product of Ca2 plus Cl minus, right? Is a greater than the hypothetical formula. So hypothetical means, like in the best situation, right? You're gonna get Ca plus Cl minus. Remember how we worked out? We got Na in the end of our final reaction. We got Na plus Cl minus.
Yep.
Right. So this is hypothetical situation where we got this exact situation.
so you
Right.
have to do two
You're
calculations.
comparing the two now. Then we got the real calculation where we got Ca2 plus Cl minus. You can see the different final energy there, the lattice energies.
You got U1 and U2.
Yeah. So now we're gonna compare those. What is the most energy? What is the most important energy term which favors calcium 2 plus rather than Cl? So basically, we'll be looking at on the lattice energy.
So you're going to work out the delta H
Yeah. And
For-
compare
for each one,
Yeah.
and then see
Compare.
which one, and with the positive, whichever one is.
Yes. And then you'll compare
higher.
both. You get it?
Yeah, so what you say, the one that's higher
Yeah.
will be favored.
Yeah.
So you've got I1 and I2. So the exact same thing.
Okay.
You've got
So this will be like a 12-mark question, because you have to do 2 calculations.
Yeah. So, but to be honest, this thing hasn't come out recently.
Okay, what's coming out?
That's the thing. I don't.
No, I'm saying like.
So
what's coming to-
these past year papers are from, like, let's see, let's go to the first one here, right? It's from 2000 and.
You don't have a latest past year paper. It's one of
I got the latest ones. I actually got hard copies without the memos. The ones currently, the 2022 and 2023, you have to pay for that. It's $20 a paper. But you guys, I told you to download the TVET app.
Yeah.
You download it.
No.
You need to get on that, huh? TVET app, Play Store.
Yeah.
You download it. Yeah, so you can see, if you look at the past year, see, this is 2013. In the 2013 paper, let's see if it came out, right?
So when you download the paper, you pay for it in the app?
No. No. But if you go now to the department one, they want you to pay. So 2013 it didn't come out, right? Let's see, 2014.
So we only got about 2013.
2014,
Huh?
nothing to say.
You got 2014 then?
Same textbook. Huh?
How are these things? Oh, it's not one of the same.
Not in order. 2012.
Yeah, I'm looking at it, 2013, 2013,
I can't see any 2014 or 14.
2012.
What page?
Still checking.
Yeah.
2013.
Okay, so in the 2012 it came out.
There's no 2014.
Yeah, it's
Huh?
2014.
There's no
Yeah.
2014.
Let's have a special textbook you also have. 2013. Oh yeah, you're right. 2013, 2012. Yeah.
That's what I'm saying, this is quite.
And then 2012, in 2012, it did come out.
Got a lot of 2012, sir.
Page number?
I'll give you now. Page 169. But the recently, that's what I'm saying. These papers are 11 years old. So I'm listening. What I'm going to do is by tomorrow I'll actually get into the newspapers. I'm trying to. It's in the app there, so we can have a look at that. My phone is not yet. You got your TV app? Yeah, you can see here in 2.2.1. What happened, guys? What happened?
Sorry.
Oh. Yeah, so in 2.2.1 you can see there, it's got the steps. Right. What is step A then, guys? Converting a solid to a gas. Solid to a gas. Kemba, let's look at page 169. Page 169, 2.2.1. 2.2.1. Right.
Which page?
169. Okay. Right. 2.2.1. We're looking at the sodium solid. Yeah. So, what type of energy involved is that? What is it called? Sublimation. Moving from a solid to a gas. And during sublimation, is any energy given off or added?
You can add energy.
Okay, sorry, it's given. Alright, let's move on to the next one. Bilal, you take this one. B.
Yeah.
Right, so we know that when chlorine gas moves through just a single chlorine atom, it's supposed to be half Cl2 there. I think the 2 is missing. But anyway, we know this type of energy is this association energy. Now, is that energy added or released? It is?
Release.